This is the day 2 presentation of section 8.5. And in this section, we're going to talk about kites. So these are kites up here. I think the cool part about this type of quadrilateral is when you think of a kite, you think you're out in a nice sunny field and a little bit of wind and you're flying a kite. And if you think of the type of kite that you fly up in the air, that really kind of looks like the same as the mathematical kite. So they're very, very similar to each other, so I think you'll find this figure pretty easy to grasp. So, tricky math question. What is isosceles triangle plus isosceles triangle? Ready for my amazing multimedia presentation. You're thinking, oh my gosh, it's two isosceles triangles added together, but it is not. It is actually called, wait for it,
Kite.
a kite, yes. Look at all the work and time I spent into that. But yeah, if you basically take two isosceles triangles and put them back to back, as long as those bases are the same length, you're going to create a kite. So that's kind of a cool deal. At least I think it's kind of a cool deal. So let's look at the mathematical definition. So basically, mathematically, we call a kite a quadrilateral with two sets of consecutive congruent sides. So I want you to think about that for a second. A parallelogram has two sets of opposite congruent sides. A kite has two sets of congruent consecutive sides. So the sides that are congruent to each other have to be like right next to each other. So consecutive means next to. So a kite has two sets of congruent consecutive sides. So basically it's like two isosceles triangles back to back. So if I took here with my purple pen and drew a diagonal here, I'd have an isosceles triangle here on the top. So I'd have the isosceles triangle here, and then I would also have an isosceles triangle down here, okay? And angles on an isosceles triangle, we had base angles and vertex angles. So if you remember, we had base angles here that were congruent to each other, and then we had this vertex angle. And then down here on this isosceles triangle here on the bottom, we had base angles. And then we had a vertex angle. So the question here on the bottom, when I ask which angles are congruent on a kite, the vertex or the non-vertex, most math students who haven't studied kites at all probably would say it's the vertex angles that are congruent, but that would be wrong. The angles that are actually congruent here are the non-vertex angles, because the vertex angle was all by itself an isosceles triangle. It was the base angles that were congruent. And if you remember the angle addition postulate, if I take something and add another angle to it, I get another angle. So I take two small angles and make a big angle with angle addition postulate. If I take this small angle here and add this angle here, I'm going to make a bigger angle. If I take that same amount of the small angle here and the same amount of this bigger angle here, I'm going to create another bigger angle. And since this has two congruent parts, as this does, that are added together, then the angles that are actually congruent here are the non-vertex angles. So a little tricky part to that. So the angles congruent on a kite are the non-vertex angles. So let's talk about some kite facts. First of all, the diagonals of a kite are perpendicular. So that creates 4 triangles inside of a kite, and those are all right triangles. So these two triangles here are congruent to each other, and these two triangles down here are congruent to each other, because you'd have, two consecutive congruent sides here. I would have a reflexive angle congruent, or reflexive side congruent here, and I've got a right angle. So these two triangles here would be congruent to each other because of hypotenuse leg. So the diagonals of a kite inside are perpendicular, create 4 right triangles, 2 sets of 2 congruent right triangles. And if you can maybe possibly remember on this other question down here, what other quads have perpendicular diagonals? Hopefully you remember the 2 other ones would be square, because square does everything. So square had perpendicular diagonals. And do you remember the other quad that had that? Well, I'm hoping you'll remember. And that other quad was the wonderful rhombus. Some more kite facts. So the diagonal that connects the vertex angles of a kite is the one that does all the work. So this diagonal here actually does two important pieces of work that the other diagonal doesn't do. The first piece of work it does is that it splits the other diagonal equally into two congruent segments. So the distance from here to here is equal as the distance from here to here. And if you look at this diagonal, this one doesn't do it. So if this diagonal does not chop the other one up equally, so this part here is way shorter than this part. So the diagonal that connects the vertex angles, first of all, bisects the other diagonal. And then it does something else that's pretty cool. It bisects the vertex angles. So this angle up here and this angle down here is getting bisected by this diagonal. And then this segment is also getting bisected by this diagonal. So the diagonal that connects the vertex angles bisects the vertex angles, and it bisects the other diagonal. And this diagonal doesn't do anything. It just sits there and looks smart, I guess. It looks like a smart diagonal, but it doesn't do anything special. A couple other facts, I guess, or at least one other fact, is that the opposite sides are not congruent or parallel. If they were, that would make this into another figure like a parallelogram. So consecutive sides are congruent, but opposite sides are definitely not, and we don't have any parallel things going on here at all. If we did with our perpendicular diagonals, we would have a rhombus, so that would not be a kite. So let's take a look at some problems. So here I've drawn a lovely kite, and I want to identify my vertex angles. So those are the angles that are between the congruent sides. So angles H and angle J are the ones that are going to be our vertex angles. The non-vertex angles are going to be the other ones. So angles K and I will be the non-vertex angles. Angles that are congruent to each other are the non-vertex angles. So angles K and I would also be congruent to each other. And then perpendicular segments, even though I don't show them, would be segments HJ. Maybe I can try to show it here with my lovely marker. So segments HJ and segments KI would be the perpendicular segments. Not my best drawing job, but I guess we'll just have to go with it. So let's try to find some math problems here involving kites. So I want to find the measure of angle D. So if you remember to try to figure out how many degrees are inside of a quadrilateral, that would be our n minus 2 times 180 formula, n being the number of sides. So we have a total of 4 sides. So 4 minus 2 would be 2. And if I take 2 times 180, I get 360 degrees. So there's 360 degrees total inside of this quadrilateral to split amongst its angles. So I'm going to subtract the 84 degrees, and I'm going to subtract the 40 degrees. Not my best writing, sorry. And that's going to leave me with 236 degrees. So that's how much is left to be shared between the other two angles. Since I have these as being my vertex angles, that means angles B and D are non-vertex, which means they're going to be equal to each other. So if I take 236 and divide it by 2, I'm going to get 118 degrees. So all I do is just take this number and divide it by 2, and angle B is 118 degrees, and angle D is 118 degrees. All right, let's take a look at this type of problem. So again, I've got a kite here, but I'm only given 2 angles. I need to figure out what are my non-vertex angles, because those are the ones that are going to be congruent to each other. So X is a vertex angle and Z is a vertex angle because they're between the congruent sides. So Z is between these two congruent sides, and X is between these two congruent sides. So my non-vertex angle is going to be angle W. So this is 110 degrees here automatically because it's going to be the same as angle Y. And then I just subtract from 360 those other 3 angles. So I take 360 minus 110, minus 100, and minus another 110, and that's going to leave me with 40 degrees. So the measure of angle W is 110 degrees, and the measure of angle Z is 40 degrees. All right, so taking a look at this problem, I've got a kite. My vertex angles are the angles here that have degree measures. So I'm going to take 360 And I'm going to subtract 95 and 35. And 95 and 35 added together is 130. So that's going to leave me with 230 degrees to be shared between my non-vertex angles. So I take my 260 degrees and I divide that by sorry, I miscalculated this. My bad. I knew I had something wrong here. I apologize profusely. So I take 360 minus 130, and I'm going to get 230. I should know that 6 minus 3 is 3. Bad Mr. Kenyon. So 230 degrees is going to be split then between x and y. So I just have to do is just take 230 and cut that in half. So that means x is 115 degrees and y is 115 degrees. Right, that takes care of that type of problem. All right, so same deal here. We want to try to figure out our missing values. So my non-vertex angles are these two. So y is going to be automatically 110 degrees. And then to figure out x, I'm going to take 360 minus 110 minus 110 minus 28 degrees. And that's going to leave me with 112 degrees. So x is 112 degrees. So this one's kind of tricky because you got to do y before you do x. But x is 112 degrees and y is 110 degrees. All right. Last type of problem involves the lengths of the diagonals. So as I alluded to earlier, is that the diagonals of a kite are perpendicular to each other. So that creates a set of two sets of congruent right triangles. So I have right triangles. These two are congruent, and these right triangles here are congruent. So if I want to figure out the length of a side of a kite, and I'm given the lengths of the diagonals, I use Pythagorean theorem. So this is going to be 4 squared plus 8 squared is going to equal x squared. So 4 squared is 16, 8 squared is 64, and added together is 80. So then in order to figure out the length of x, I'm going to take the square root on both sides of these. So I need to figure out the square root of 80. So the perfect square that goes into 80 is 16. Oof. And 16 times 5 is 80. And the square root of 16 is 4. And the square root of 5 just comes along for the ride. So the measure of x is 4 square root of 5. Okay. Last problem. So in this case, I want to figure out x and I want to figure out y. So you'll notice here that I've got a diagonal length of 3 and 3, and because this one is connecting the vertex angles, that would make this measure here as 3 as well. So to figure out x, this would be 3 squared plus 3 squared equals x squared. And then to figure out y, because I think I have them both showing at the same time, y would be 5 squared plus 3 squared is going to equal y squared. So this is what I'm left with when I do the math part of it. So 3 squared and 3 squared. Hopefully you recognize that this is one of the world famous K-Blusky 45, 45, 90 triangle roadmap triangles. So perfect square that goes into 18 is 9 in 2 is what's left. So this is 3 square root of 2. So again, the world famous K-Blusky 45, 45, 90 triangle roadmap says that the hypotenuse is square root of 2 times the leg. So this is 3 square root of 2 for x. And then for y, I've got the square root of 34, and I can't simplify that. The square root of 34, there's no perfect square that goes into it, so it's just square root of 34. All right, so that takes care of this presentation. So what I want you to do on Friday is do problems number 2 and 17 through 20. Keep that assignment. Don't mail it to me. Just hold on to it until Monday. On Monday, I want you to do problems 21 through 23 and 35. And then when you've got both of those sets done, you can send them to me in an email. And thank you for watching this presentation.